Okay, I'd like to welcome Jamil Appa. He's the director and co-founder of Zenotech Limited. I'm sure he'll introduce the company, but it's a company that's based down in Bristol that does a lot of work with CFD. So over to you, Jamil.
So I'm Jamil Appa. I'm co-founder of Zenotech, and I'll be talking to you today a little bit about some of the challenges I suppose we faced in developing one of our products, which is a CFD tool, which uses a whole raft of different parallelization techniques. My personal background is, I suppose I'm coming to this from very much from a sort of an engineering point of view, and fell into the computer science piece. But my colleague James Sharp, who has contributed to this talk, his background is computer science and math. So as a team within Zenotech, so we're 6 strong. And as Tom pointed out, we're based in Bristol, and we have a combination of computer scientists, engineers, mathematicians, physicists. So we're quite a mixed bag. We started off in 2012, and all our backgrounds, I suppose, are from the aerospace and defence sector. And sort of brought the team together sort of the 2 of us started in 2012, and so we're gradually bringing the team together over since then. We have 2 main products. One of them is the CFD solver, which I'll be talking to you about today. And our second product is effectively, the best way of describing it is it's a portal to HPC cloud. And by HPC cloud, I mean in its broadest sense of the typical cloud like AWS and Azure, but also some of the academic supercomputers as well. So we broker access, commercial access to those types of facilities. So on the CFD front, we very much were working, so the team brought together was previously working within sort of the aerospace and defense sector, developing these types of tools for an internal customer. So for the engineers to use internally within the organization. And we sort of had the thoughts of actually the kind of techniques that we were developing would be of use and of interest to a wider community than just the aerospace and defense community, and hence the reason for starting up Zenotech. And I had the pleasure, I suppose, of starting with a totally clean sheet of paper in 2012 and writing something from scratch, which is very infrequent, I suppose, in the world of sort of HPC and these types of bits of software. So we sort of decided to pull together the best-in-class algorithms, and really with a view of trying to make sure that we were, I suppose, as future-proof as possible. So given it was parallelism is sort of the key to keep things going forward, and it's just how do we express that parallelism in such a way that we can take benefit of whatever comes next, because there's going to be new frameworks and new processes coming out. Is making sure as best as we can is to lay it out in that sense. Just to give you some examples of what I mean by CFD and complex CFD, it looks like a simple example. It's flow over a building, and that's relatively simple geometrically, but the physics of the flow is really complex. And this is sort of a particular case that we've been testing. And this particular solver that we're running here, we're using a discontinuous Galerkin high order formulation, which we're solving in this particular case. I suppose it's similar to what you've seen from the Met Office, but discontinuous Galerkin is sort of it's the halfway house between finite volume and full finite element, is probably the best way of describing it. Give you another example. This is flow over the landing gear of an aeroplane, and this is the kind of things the way we would be solving these types of flows with a view of trying to predict the acoustics, the noise being generated from these types of structures. For aircraft, actually, when they come into land, most of the noise that you hear as they come in is actually not from the is not from the jet engines anymore. It's actually from everything else that's hanging off the aircraft that it needs to hang off when it's coming down to land. So undercarriage flaps and the like generate the bulk of the noise as it comes into land. So being able to sort of predict and design these entities is important, and these kind of calculations do take a long time, partly because they have to be time accurate and solving acoustics on them can be time consuming as well. Here's something slightly simpler, but with more complex physics, I suppose, involved in it. This is a vortex hitting a shockwave example. It gives you some nice flow features as things sort of all mix, and you've got shockwaves going all over the place. Again, these are sort of these high-speed flows are important in certain industries as well. So it gives you an idea of the kind of range of things that we do, all the way from low speed flows around buildings, all the way to more high-speed flows, I suppose, which you can see here. And this is all encompassed within a single solver. So it's making sure that we've got all the right algorithms in that framework to allow us to solve that range of speeds. Is key. So into a little bit more detail about the code itself. So obviously, when I first started out, C++ 11 had just hit the streets, and the support from the compiler support for C++ 11 at the time was patchy. You were still having to use sort of various C++ compilers and boost components to try and get up to what was being offered in C++ 11. Obviously, since then, C++ 17 has come out with a whole bunch of new additions as well. So I would say the core of our code, we do make use of some C++ 17 features, but it's not huge. We're gradually migrating across to that. But the core is all written in C++. We front all of that with Python, and that's purely for ease of integration into our customers' processors. But it also, in terms of from a usability point of view, it allows our users effectively to customize what we're doing relatively simply, because it's sat within with Python. We've just very recently actually moved across to Python 3. That was a little bit of a headache, but that's done now, and that works nicely. And yeah, and just for information, we use Boost Python as the means of gluing the two together, and we find that works really well. From a parallel point of view, we make use of MPI for sort of multi-process parallelism, and we tend to run, this is not sort of enforced on the users, but mostly by default, the application runs one MPI task per NUMA region, which previously that was one per socket on the CPU side, but obviously with the new AMD processors coming out, that's a little bit more complicated. Or we use one MPI process per device if we are targeting GPUs, for example. So that's the typical way we would the application would start up. We also make use of a library called NICL from NVIDIA, and when we're running on GPUs, we use that library to do inter-GPU comms. Two reasons for it. Obviously, one of the bits it is highly tuned, obviously, to make use of NVLink between the GPUs when you're on a node. But also, it will offload. It will do RDMA over using GPU Direct over the network as well. And that then actually doesn't require us to have our MPI layer effectively CUDA aware. So you can mix and match NICL and MPI, and they do work nicely together. So your MPI layer can be very generic, and you can leave sort of the GPU aware part of your communications off to NICL. And that does become, for us, at least where we're trying to distribute this code commercially, the portability of those distributions becomes important, and trying to make sure that your MPI distribution that you have is portable and supports things like CUDA is, at least today, a bit of a headache. So actually the combination of these two actually delivers that requirement. Once we're within an MPI process, we use a combination of threads, and beneath that we then use OpenMP or CUDA, depending on the architectures that we're targeting. And the reason for sort of fronting everything using threads is it allows us to decouple certain operations. So, for example, to allow us to overlap MPI operations with other compute. A lot of our MPI traffic is happening on a dedicated thread, so it allows us to do some overlapping. But also, it becomes helpful for other things which are happening within the solver to allow us to overlap tasks which are happening. I'll come back to some of the headaches that brings a bit later on. But yeah, so you've got parallelism from an MPI point of view, you've got parallelism from a threads point of view, and then below that you've got parallelism from an OpenMP or CUDA point of view, and I suppose you could go down one level deeper than that, and you've also got vectorization under the hood as well. We've got minimal device-specific code. I'd say we haven't got a huge number of lines which are sort of very specific to one architecture or the next. So, for example, CUDA's kernel syntax, or even some of the OpenMP pragmas, they're not sort of liberally spread around the code. We sort of hide that away from the developer. I suppose in a similar way to the talk from the Met Office around the separation of concerns, we try and separate out the complexity sometimes of targeting specific hardware from the algorithm itself, from the mathematics. Things like GPUs, it uses runtime introspection, so it actually goes in and has a look at the kernels to decide on the launch parameters that they use for those particular devices. And we're using a lot of the mechanisms of C++, I suppose, to allow us for the compiler to do the heavy lifting. So these code paths, whether the CUDA code path, the OpenMP code path, is built and compiled into these libraries. And that is basically down to depending on which compiler is being used. So if you're using NVCC, for example, it will compile the CUDA code path. If you're using, and we don't use the Intel compiler, if you're using the Intel compiler, it'd be the OpenMP code path, which is done, and that's just done automatically behind the scenes. So the compiler is doing a lot of heavy lifting for you. Again, starting in 2011, we were just using sort of functors. Lambdas were starting to appear with C++11, but yeah, we use sort of a func to lambda pattern to inject these parallel kernels at compile time into these various code paths. So again, all of this is being done being done by the compiler, and deciding which ones to pull in at which time. We do have a few device-specific parallel kernels. There's some cases which it's just not possible to write something which is totally generic. I'm trying to think of things like where we're doing sort of parallel summations and trying to sort of maximize accuracy when we do those summations, and we're doing we have to use Kahan summation to try and reduce the error there. That's quite hard to do in a totally generic way. So we do have a few specific kernels, but in most of the kernels, and we're talking here of order of several hundred kernels in one of the solvers. Are all generic, and they're generic whether they're OpenMP or being run through CUDA. It's the same piece of code, and I'll show you an example later. This issue of memory spaces, when you're talking about being able to work with multiple devices, and we handle different memory spaces by storing multiple pointers to the different memory spaces. So we've got this concept of, I suppose it's coming into data parallel C++, concept of a multi-point, which points to different memory spaces. And again, the compiler, depending on the code path it's compiling for, will use the appropriate version of that pointer for the memory space appropriate for that particular code path. So again, the compiler is doing the work of deciding which one to use under the hood. The developer doesn't see any of that at all. And the other issues which tend to hit us is things like memory layout. So things like when to use an array of structure and when to use structures of arrays. And again, these things, depending on architecture, actually then depending on the algorithm that you're using as well, vary. And that again can be runtime configured using traits. So again, these traits can be dependent on the path that's the code path that's being compiled for. And you can make these decisions. So for example, padding and alignment and all those kind of things which you might, which are important when it comes to performance and vectorization, is all decided for at compile time. So we do rely on the compiler doing a lot of heavy lifting work for us. Just a few facts and figures. Yeah, we use, as I mentioned, we use the Intel toolchain, and very much that is for portability. So one of the issues with trying to use some of the other MPI implementations, for example, their portability between different systems is difficult because they tend to sort of link into very specific, especially InfiniBand libraries, which you can't then take from one system to the next. So the Intel toolchain actually gives us that portability between different systems, and that works great for us. The other beauty that the Intel toolchain delivers is from a SIMD point of view. It allows us to target multiple architectures, Intel architectures, within one executable. So it will then automatically choose the vectorization, which is appropriate for the underlying hardware that's being run on at the time. And that's a great bonus for us because we don't have to then compile a huge different number of variants of the code. We can deliver a single code which allows us to target a huge number of architectures automatically, and it does a reasonable job at trying to decide which is the best vectorization support for various parts of the code to deliver. One of the other things we do, we independently build all the dependencies. So we have control over all the build parameters, and again, I'll come back to why that's important in some of the challenges that we have a little bit later. But it does give us then the ability to sort of lock down on build parameters and versions, and we build things all the way from Python to even OpenSSL, because the systems that we're delivering the code onto don't necessarily have these types of libraries which are up to date. So we carry all of these things with us. Just to make sure that we know which versions we are. So if something does go wrong, it is truly our fault. It's not something which is due to a particular version of software on the end user system. And from the build point of view, we use Bazel from Google in combination with CMake and Ninja on the build side. And the combination of all of those, I think from a parallel build point of view, gives us the right features. So Bazel gives us sort of the hermetically sealed builds, so we know exactly what we're building. Ninja gives us the parallelism, the build parallelism piece. But yeah, just to give you an idea, so if we're building, and we build things like ParaView, we're building the Trillanos libraries. So these are the two big ones. Also with all our solvers as well. It takes around an hour to build on 56 cores. So there's a lot being built each time. Test cycles that we rerun on Jenkins can take up to 24 hours, depending on how busy various clusters that we use to test on. And once you've packaged everything up, including all the runtime dependencies from the likes of Intel and MKL and all the CUDA dependent and all CUBLAs and everything else that comes along, you have a tarball which is about 2.5 gigs in size, so it's not insignificant. But yeah, some of the and it's less our code which is big. It's actually a lot of the runtime libraries. So the runtime libraries which come with CUDA and the Intel toolchain do consume a huge amount of space. But just to give you an idea, it gives you an idea of the kind of size. We also on the container side make use of Singularity sometimes when trying to make sure the end user, the support on the end user system doesn't quite match. We can deliver things in containers as well. Just to give you a quick idea of what sort of the code ends up looking like. So this is, if you look at it, to be honest, it looks as much as C as C++. But just take you down there. So, for example, the model constant that's actually expands into a macro. Obviously, on the likes of on GPUs, there's different memories. There's constant memory. There's local. There's shared memory. There's global memory, and the constants that we use within the solver on the GPU at least are mapped into constant memory. On the CPU side, it's just a constant which is declared within the solver. So, depending on the code path, the compilers which are coming down through this, that model constant macro there will target the appropriate memory to pick out that constant. So that's one example. Obviously, you can see the SIMD alignment there, keyword which is being used. Again, that's something which is expanded depending on the code path. That align as keyword obviously is important on the CPU side, but not on the GPU side. But then everything else in terms of the loops that you can see below, effectively hidden behind the scenes are C++ operators. But as you can see, they effectively, for all intents and purposes, appear as normal sort of array accesses. But interestingly, behind the scenes, we can change the layouts of all of this memory, from array of structures to structures of arrays. We can change the padding, and again, we can change the alignment. But from the scientist sort of developer point of view, this code stays exactly the same. So we're sort of trying to get to the point where, yeah, you write it once and compile it multiple times, and target the appropriate hardware accordingly. But yeah, that gives you an example of what the sort of the code under the hood looks like. So coming to some of the challenges that we face in terms of developing this, as you can imagine, as I've already mentioned, we're putting in quite a few third-party libraries, and especially when it comes to OpenMP, and to be honest, the same is true of MPI. Ensuring sort of consistency of the use of OpenMP can be complex. So, for example, if I downloaded the Tridinos library, and let's say it was a pre-built version of it, and they had built it against libgomp, and I was using the Intel version, libIOMP, you run into all sorts of issues. So we're in a lucky position at the moment of being able to compile everything and having control over the build parameters of all these third-party libraries. But there are cases I can see coming into the future where we're going to be wanting to use third-party libraries which come pre-compiled, and making sure that these things are consistent can become more and more complicated. So dealing with that is something of a challenge. We've also found using some of the OpenMP SIMD features does interfere with sort of the automatic vectorization in some compilers. So you don't sort of get the consistent use of that. So we've actually turned off the OpenMP SIMD features because it seemed to be conflicting with some of the optimizations which were happening by default in the compiler that we were using. So that's an interesting one that we've sort of come across as well. And then obviously controlling OpenMP use from multiple threads. As I mentioned, we use sort of threads at the top level. And if you imagine if you have OpenMP loops being launched in two of those threads separately, you can obviously you can exhaust all your resources because of it, because they'll quite happily run. Interestingly, it'd be interesting to see how the developments in SYCL and SYCL queues actually may end up being a solution to this, because then you're relying on SYCL to take a little bit of that management overhead away. So so that'd be an interesting one to keep an eye on. A few more challenges, and for very tight loops with variable trip counts, yeah, load imbalance. And I think some of the questions that came up in the last talk were sort of alluding to this. Yeah, the overhead of creating these open loops. So how do we deal with that? Yeah, and one-time scheduling using environment variables. As I said, we've got 200 odd kernels appearing in this application. Actually, trying to control all of that using environment variables is just not possible. It's not something which works. So having other ways of being able to schedule these OpenMP loops, or controlling the scheduling of these OpenMP loops would be of interest to us. I think for the last talk, effectively answers that's the third point here of having more loop scheduling schemes. And I think that's something I think we'll have a look at the LB for OpenMP library to see how this works. So our loops tend to be they can be imbalanced, and also you have certain loops, and actually again in the Metal story we're talking about multigrid, where you have certain kernels which are used over different meshes. So you have the same kernel being used at one point on a very fine mesh, and then suddenly it's being used on a very coarse mesh, and making sure that you've got the right scheduling algorithm that allows you to span those different scales of loop size, but also and balance as well. So the balancing might change as well between those two. So being able to do that dynamically in some way, or being able to have the logic to express that is something of interest. And it also would be good to sort of have Pragma-based support to change the algorithms, as I was sort of mentioning there, is to somehow add this ability to add more logic in some way. I don't know quite sure how you do that. Whether you can do that externally, or be able to use the pragma to point to some other logic, which allow you to help you to decide. I suppose it's in a similar way to the way that we tend to use on CUDA, where we're using sort of runtime introspection to sort of look at what the kernel's doing. We know what the sizes of the loop is going to be, and then make a decision at runtime. So maybe the ability to sort of do that, to deal with those kind of complexities. Obviously, that OpenMP has an API to do that, but it's whether you can sort of express that using the pragmas would be of interest. Yeah, other than that, those are all my challenges for the audience. Any questions?
Thanks a lot for your talk, Jamil. That was really interesting. In particular, the list of challenges that you're facing, and how maybe some of those might be solved with OpenMP, like the meta directives or the variants that you were alluding to at the end. I think we'll, in the interest of time, ask you to take some questions in the Q&A over text, if that's all right.
That's fine.
That's brilliant. Thanks a lot for your talk.